Okay, welcome to this presentation. I'm Qiang Li. I'm from Group, and I'm the developer and maintainer of the Kata Containers. And I worked in Group for the Kata Containers developing and also maintained the Group's container infrastructure. And today's topic is about how to enhancing the container securities with the Kata Containers and the eBPF at Group. First, I will give a simple introduction about the container security requirements and the challenges we met. And then I will give a simple introduction about the current implementations and the issues. Third, we'll give our solutions. Then I will give a lab demo. And last, I'll give some performance data we tested in our company. Now first, let me introduce the container security issues. As we know, the containers security issues will split into two parts. First one is the image scan. This is also called the static scan, which we will scan the malicious programs or the other malicious scripts in your image, in your container image. And then the second part is runtime audit or runtime security, which we call sometimes when you run the containers, you will meet some issues such as the malicious programs running in the container, or you download some malicious scripts or some malicious programs from the website and then run in your containers. And the third way, we will trace how the programs run in your containers, such as the programs you run and the network port you access and the other issues. So this presentation is mainly focused about the runtime audit, runtime prevention issues. The traditional implementation of security issues we met in the container security, in the container scenario is all about such this is the traditional way they will enhance their security with on the container. They will use the code modules such as the static and others. All they use the eBPF to audit or trace their programs in the container. But this will meet some issues, such as for the traditional container, they will the code module they will load in the node, and the entire node containers will match or they will aware the code module's actions. So this will bring some issues, such as if you the code module you have some bugs or any other issues, it will impact all the containers on the same node. And also, for the eBPF issues, it's also the same things. So if you run multiple container services on the same node, such as the online service or such as the the batch computing tasks, and this they will meet not the same issues, the same security issues. For example, in group, we will use one node to run many tasks, and these tasks are fall into the three classes. For example, the first one is about the agent AI sandbox tasks, and the second one is about the batch computing tasks, and the other one is the online services, such as financial technologies. We use some transactions programs, and those three classes they met the different security issues. But if you use the traditional security way and you use the kernel modules or the eBPFs in the single node, and they will communicate with each other. For example, in the sandbox agent, you can't you will block some of the program to access some website or some network port, but the other programs, the other container tasks, they will allow to access those sites. So this will conflict with each other. So this will can bring these 4 faults. The kernel dependency. So as I said, if you use the eBPF, then the eBPF will be dependent on the kernel versions. If your node run a very old kernel, but you don't have time to upgrade your kernel to support the eBPF version, so this is a bring analysis. And the third one is will face the large attack surfaces. If you use the kernel module or the eBPF in the entire node, then the entire node will bring the large attack surface. And the third one is hard to enforce. So as I said, if the container one they want to block the connect to the network website, but the batch computation you would allow to, then you can't enforce to the security policy to apply to all of those tasks. So how do we solve these problems? We use Kata Containers plus eBPF. Then I will give a simple introduction about what is Kata Containers. So what is Kata Containers? Kata Containers is used the virtual machines to bring the containers to run as the traditional containers first, but it will compatible with the containers interface such as the Kubernetes and Docker. It will compatible with those container systems. But also we use the virtual machines to embed the containers to run, and this will isolate the container from each other on the same node. And this will bring a benefit to us is that every container will use a separated kernel. We call it a base kernel. So that if we load the eBPF into the containers, we only load the eBPF into this port base kernel, and the host kernel will not be affected. So this will bring us the 3 benefits, and the first is security isolation. And Kata Container also bring us the resource isolation. What is resource isolation? Because we know the traditional basic containers, they share the same kernel, and they use the C groups and namespace to separate each other. But they also share the same logs in the kernel, in the same kernel. So if there are some bugs in the kernel, and one container will trick the issues, then it will block all the other programs on the same node. And the third one is the fault isolation. Just as I said, the Kata Containers, it will use a separated guest to isolate each other. If one program in the container, they tricked a fault, and this fault will only occur in this VM, and it will not affect each other. And the other is where we use eBPF and where we don't use the kernel modules. And think eBPF is not is very familiar with each other. eBPF, it will bring, I think, will these four benefits to us. The first one is security. Compared to the code modules, if you there are some bugs in the code module, and that will be crash the entire kernel. So, but eBPF it will be audited when you load into the kernel, and it will be check the eBPF programs to make sure there's no fault, there's no dead loop. So they will make sure the eBPF program is security. And the second one is flexibility. eBPF allows program to be dynamically to be load and unload from the kernel module and it will give us the flexibility to change your programs, your security programs online. And the third one is very lower overhead. Why we call it the lower head bring to us? The first one is that eBPF programs run in the kernel space, and it will provide high process speed to block or to audit, to trace your actions in the guest kernel. And the fourth one is programmability. The eBPF can bring us to program the complex logic to prevent or to audit or to trace the event in the guest kernel. So we bring the Kata containers and combined with the eBPF, it will bring us those benefits. It will give us the strong isolation and app policy and individual kernel. So there's no, if your node runs the older kernel, there's no need to upgrade your kernel to match the eBPF requirements. And the third one is verified before load. As I said, the eBPF will be verified before you load into the guest kernel. And it will also bring us the flexibility strategies, as I said before, and high performance, etc. So this is the high level of the architecture of our security program or architecture. The first, the security engineer will be write the security policy, and the policy will be adopted or deployed by the Kubernetes. And there's a security agent on every node. They will receive or scan or watch the policy issues, and when they found the policy change, it will receive this signal and will download the security policy from the server and will apply it to the specified Kata containers. And also, when we load the eBPF into the Kata containers, and we'll also to load the policy into the guest to enforce the programs to adopt this issue. And we also give some logs out how the programs run in the container, such as the programs you run, the syscall you adopted, and the files you accessed, and the network you connected, and those will be logged out, to give us to treat or to audit the activities occurred in this container. And this is the architecture of the Kata containers to deploy the eBPF. As I said before, the Kata containers use machines to include the container. But how do we load or unload the eBPF from the host to the guest kernel? And this will bring us the complexity. So we deployed or we programmed what your eBPF, just like the VM's what you blocks or virtual network. And this will split two parts in our Kata Containers. And the first one is the eBPF server in the guest kernel. And this is the second part is the eBPF backend in our VMM hypervisor. And when we load eBPF from the users, then the security agent will get the eBPF program and policies and will load it from here to the guest kernel. And the trees or the issues or the logs will be shared between the guest and the VM through this Ring buffer. And this will bring the very fast performance, since if we don't use the Ring buffer to share between the guest and the host, we have to use some other way to copy the trace logs of data from the guest to the host. And this will bring us much CPU overhead and issues. So we just use this Ring buffer shared between the guest kernel and the VMM. Okay, next I will give a lab demo. I don't know, the lab demo always, maybe often floppy. I think it's floppy earlier and floppy often. So I'll give you a simple demo. First, I have logged into our demo machines. And I will show you the security policy we defined here. This policy contains 4 parts. Can you see it clear? Is it okay?
Yes.
Okay. This part is we call the drift prevention. Next, I will give a detailed discussion information about what is drift prevention. This means that if you download a program from the website or other site, and it will be blocked from running on your containers. This means that you can only run the programs in your container images, and if you download one from the other parts into the container, you can't run it. And the second part is process block. That means that we can block what programs you run and not run. This means that with normal action with block, and here means that the wget binary will be blocked if you run it. And the third one is network port, and this means that the 80 port will be blocked if you access. And also here you can also specify which programs can be in the whitelist, which will not be blocked. Here I just ignore it. So this means that every program can be accessed the 8 port. And the fourth one is that domain name, which means that here means it's a white list. This means that here we only specify the endgroups.com is split, and the other domain name will be blocked. You can't access them. Okay, here I just EAC into a container, and here the container hasn't been loaded any security policies. So I can show you, you can access or run anything. If you run wget, here means that you can run it successfully. And if you access the end group domain name, yes, you can run the wget and also access the end group's 8 port. And also, if I if I write a script, sorry. Okay, okay, here means I can run the script successfully. Then let me load I load this policy into this pod, and then let me ease into the container. If I run the wget and groups, okay, here means that the wget can be blocked and there's no operation to permit it to run the wget. This means the policy has been applied. Okay. Also, if you run the script as right, oh yeah, it can be permitted. It can be run successfully. So this means that our JavaScript provision has been applied. And if you want access the 8 point here, also it will be also be blocked by our policy. So as an operation not permitted, you cannot access the 8 port. If I change it to bottom port and you can access it successfully. So the 8 port has been blocked. Okay. The demo is that okay, the demo is over. Then I will give an introduction what those policies will mean. Just as I said before, the security agent here, it will watch the policy changes from the Kubernetes server, and when the policy changes, it will get the latest policy from the server and it will load into the Kata pod. First, it will load the eBPF program here, and we will split those programs into 3 parts. The first one is syscall. We will trace or audit the syscalls you run in the containers, and we will use RSM to prevent the syscalls or other network access from your access. And the third is network part. So, as I said, how the eBPF program to implement the network prevention. Now first, it will load the eBPF and will be verified in the eBPF runtime, and it will be applied into the eBPF's TCP program, and other RSM programs. The RS programs will be used to prevent the domain name and the port and the others you can't be accessed. And the TC program will be used to prevent specified with IP address and the IP address corresponding with the port that the file tune that specified the destination that you can't access or you can access. And the second way is the file access control. This is used to prevent the file you can't access or you can't access. And the eBPF program will be monitored every file's inode in the guest kernel. And once you specify such as the file A will be blocked by access or by read or by write, then the eBPF program will copy the file's inode into the eBPF program's maps. And then once users want to open these files or write these files, it will be blocked by the eBPF in the RSI mode. The next one is the syscall monitored in our security issues. And as I said, you can block the specified syscalls from open, such as the open of a file or read of a file, and or ENC other programs in your containers. And the last one is the block the drift preversion. As I said before, what is the drift preversion? This means that the Kata containers it will apply the static scan and will only allow the programs in your container images to run. If the programs you download from the online site or from others, so it will be prevented running in a container. And this will block some malicious issues, such as the hackers will write or download some malicious scripts from their website and they will run in the containers. So this will block them to run. And only the scanned the programs in your container images can be allowed to run successfully. So if you load the eBPF program into the guest kernel, will impact your program performance. Here we give some sim test about the performance data. Here, this is about the TCP's performance test data, and here is the UDP's performance data. Here, this black bar means this red bar means that there's no eBPF was loaded into the containers, and this means the time the TCP connection used, which means here is the 331 microsecond. And this one means that when we loaded the eBPF into the guest kernel, but there's no policy enforced into your container. And here we can see that the time used only small above the non-eBPF. This means that the eBPF program didn't impact your TCP connection. And the green bar means that you not only loaded the eBPF, but also you have enforced the policy to check which the TCP you connect or can't connect it. And we can see that the time also only improved very little. So this means that the 3.61 microseconds only small bigger than the 3.31.27. This means that the eBPF program will bring no impactions to your TCP's connection. And here this means the UDP connection, UDP connection connect performance data. We can also see that they only improved from 4.12 to 4.31 microseconds. So this means that the UDP is also impacted. And this one is the CPU utilization. As we know, you loaded the eBPF program into the guest kernel, and every hook point will be run the eBPF in your guest kernel. And this will bring some CPU usage in your guest kernel. So how the CPU utilization will be improved once you loaded the eBPF on the and enforce your policy? Here means that the CPU utilization only improved from 28.79 to 29.21. This only improved not 1% in this case. And also the UDP case is impact very bigger than the TCP connection. Here we can see that it improved from 24.49 to 25.37. And from here we can see that our eBPF and policy will not impact hardly to our programs. And this performance data is that we test how the programs or the process run when we loaded the eBPF and enforced the policy. And the red part, red, green, and the purple bar means that the programs, your EAC programs from the start to the end of the EAC, and will use the time. And we can see that the entire part, or the almost entire part, is the EAC used, and only this the small part here. This small part is that we loaded the eBPF program and enforced the policy cost the time. So we can see that the eBPF will not impact the program's run in your container. All right, we and group had collaborated with the Kata Containers community to launch the white paper to show how we use the Kata Containers to secure our programs in Ant group, and we have launched the white paper in the Kata community, and also this also will be adopted by the eBPF Foundation in their example usage. So you can download or access those white papers from the Kata website or the eBPF website. Okay, if you want to access the white paper, you can quickly access it and scan this QR code to access this paper. Okay, that's all. Thank you.
Could you flash that QR code up again, please?
Mm-hmm.
The QR code. Can you?
When is going to be implemented?
You can access.
Is it implemented already?
It is.
Mm-hmm.
It is working with Dragon Ball.
Yeah, by now it will work with Dragon Ball because we have added eBPF backend into the hypervisor.
Which hypervisor?
Dragon Ball.
Dragon Ball.
Yeah, Dragon Ball. Yes. And I think we will to bring it to the cloud and factor, but human is not that. Yeah.
Thanks.
For sharing the ring buffer between the host and the guest kernel,
Remember?
It's just
Yes.
do you also need modifications on the guest kernel, or is this something that upstream Linux supports? You can decide.
Okay. Here we have eBPF server here. Once we loaded the eBPF program from the eBPF backend, and we use the vSOC to communicate the eBPF server and to tell it where to load the eBPF, and then we will vSOC to share the eBPF ring buffer access from guest to host, and then we will access or read the eBPF programs from the ring buffer.
Thanks, makes sense.
Yeah, very simple.